The ocean covers 71% of the Earth's surface and contains 97% of the planet's water. Is it any wonder then that it plays a vital role in many of the Earth's systems and processes? Life continues here on Earth because of a fine balance of natural systems known as biogeochemical cycles. The atoms and molecules that are the building blocks of life are circulated from non-living or abiotic things, like rock and air, into living or biotic things, and back again. These biogeochemical cycles include the water cycle, the nitrogen cycle, the phosphorus cycle, and the carbon cycle. The molecules that are needed for the life processes of all organisms, plants, and animals contain carbon as their main structural component. 121 times 10 to the 15th metric tons of carbon are continuously being cycled throughout the Earth's geosphere, hydrosphere, atmosphere, and biosphere. Some of this carbon recycling happens relatively quickly. As a carrot grows, it removes carbon dioxide from the air, and through the process of photosynthesis, releases oxygen and uses the carbon atoms to produce the carbohydrate glucose. Glucose is stored in the carrot's root and converted to starch and other carbon compounds. When a rabbit eats the carrot, digestion transfers carbon compounds from plant to animal. When the rabbit needs energy, it gets it by metabolizing carbon compounds stored in its tissues. When it defecates or dies, the carbon from the carrot is transferred back to the atmosphere in the form of carbon dioxide, or back to the soil, where it's converted by other organisms that release carbon dioxide in the process of respiration. This is part of what's known as a fast carbon cycle. Other times, the recycling of carbon takes hundreds of millions of years. For example, oil. It's the remains of marine plants and animals that lived millions of years ago. When they died, their bodies sunk to the bottom of the ocean. Bacteria decomposed them. What was left was mostly carbon and hydrogen. Over time, the remains were covered by layers upon layers of silt. Pressure and heat built, changing sediment into rock, and the remaining compounds into the hydrocarbons that we know as fossil fuels. When we combust fossil fuel to power our vehicles, the carbon from plants that died millions of years ago is released into the atmosphere. That carbon dioxide joins carbon monoxide and carbon dioxide released from volcanoes, wood fires, the respiration and decay of plants and animals, even the breath we exhale. Plants, especially trees, take in carbon dioxide from the atmosphere, and the cycle begins again.
But plants can't absorb all of this excess CO2. In fact, atmospheric CO2 levels are higher than they've been in at least 800,000 years, and they continue to rise. The oceans play a vital role in Earth's carbon cycle, constantly absorbing CO2 from the atmosphere. Carbon dioxide is very soluble in water. As atmospheric carbon builds up, more carbon dioxide dissolves into the uppermost layer of the ocean. This layer of the ocean is home to tiny, mainly one-celled organisms called phytoplankton. Just like trees and plants on land, phytoplankton, or ocean plants, also produce oxygen through photosynthesis. In fact, they produce over half of the oxygen that we breathe. Without them, we wouldn't exist. As the oceans take in more and more carbon, the phytoplankton use it to multiply in what is known as a bloom. Some of these phytoplankton blooms are so huge that they can be seen from outer space. Phytoplankton form the base of the ocean food chain. They become food for animals that are in turn eaten by larvae and by krill, transferring carbon from plant to animal. An array of mollusks, cnidaria, crustaceans, fish, and sea mammals join the feast. They send carbon down through the ocean layers as they defecate. Tiny diatoms and mollusks fix more carbon in their shells in the form of calcium carbonate. When they die, their shells sink to the ocean's bottom where they form sediment. The limestone will rest on the bottom of the ocean, storing carbon. After millennia, these carbon-bearing rock layers may be carried down to the Earth's interior at subduction zones. Volcanoes release that carbon into the atmosphere as part of the slow carbon cycle.
This is just part of the story of how the ocean is a carbon sink.
Seawater has an extraordinary buffering capacity, meaning that as CO2 is absorbed into the surface oceans, it's immediately converted into carbonic acid. That acid is then essentially mopped up by the carbonate ions that are contained in seawater. Of course, this comes at a cost of those carbonate ions. Carbonate ions are important building blocks for coral reefs and also for any animal that builds a shell in the ocean. Here in the lab, with the water sample that I took earlier, we're able to measure pH, which gives us an indication of how much CO2 is in the seawater. I'm going to add an acidic indicator dye. So this seawater sample is around pH 8, which is good for the oceans. But a more yellow sample indicates that the seawater is more acidic, which means that there's more CO2 in that surface ocean. Runoff of nutrients like nitrates and iron combined with the CO2 that's in the surface ocean leads to bigger phytoplankton blooms. And phytoplankton blooms are not great for the marine ecosystems because the phytoplankton eventually die and bacteria eat them, and those bacteria consume all of the oxygen that other animals need. This leads to disruption of marine food webs, and this ultimately will affect every ocean process that we depend on. For now, as scientists, our greatest hope is that we can continue the research that we're doing to better understand the role of the oceans in the carbon cycle and how it's going to influence all life on Earth.